All right, this is going to be our lecture on Chapter 6, titled Mole-Mass Relationships. So you might want to follow along in your notes. Definitely make sure you take notes just as you would if you were in class. Write down questions, things of that nature. Because we are starting a new chapter, I'm excited to tell you about this hike. This is actually one of my very most favorite hikes in all of Arkansas. You got some pictures along the hike here. It's known as Indian Creek or Eye of the Needle. I'll have the title listed in a second. But along the hike, which is kind of a down and back style hike, you will run into these really cool waterfalls. This first waterfall on the left is actually coming out of a cave. They call it Arkansas Cave. I always try to kind of, does this look like an inverted Arkansas to you? Anyway, so you see this waterfall, you see another waterfall. You can actually see both of these at the same time. When you're standing looking at Arkansas Cave, you can turn to your right. And just for scale, I always make my photo prop stand there so that you can see how big the waterfalls are. And anyways, you see these waterfalls. This is not actually the grand finale of the hike. You keep hiking. You have to do a little climbing. So I probably would not recommend bringing pets on this hike. It is a very beautiful hike, though. Most of it's pretty flat. But at the end, you do some climbing to get to the grand finale, which is this massive rock structure right here. So the hike, I said, is called Indian Creek. The nickname for the hike is called Eye of the Needle. And you can probably see why the rock structure kind of looks like a small eye of the needle there at the top. It's really massive. It's hard from this photo to obviously convey how grand it is. So I always put this next photo too so you can maybe get some context. Here's me at the bottom. I didn't climb very far, but really, really big. So we stop and eat our lunch here, and then we'll hike back after resting up. There's the name of the hike. You can access this hike in the Ponca Buffalo River area, specifically if you go park or camp at Kyle's Landing. Okay, which is a very popular campground. It's a popular spot to get in or out of the river. The trailhead is at Kyle's Landing Campground. It's a great campground, really clean, really nice. So fun for camping or to do some hiking. I would definitely plan all day if you want to go do this hike on fall break or any time of the year in which hiking feels good. But it's a couple hour drive there. The hike's going to take you several hours to do, and then you'll have a couple hour drive back. So hour and a half, less than 2 hour drive for sure. But anyways, there's my favorite hike. Okay, let's get into chapter 6, mole and mass relationships. This is a shorter chapter, but it's pretty math intensive. So if you don't have your calculator, if you don't have a periodic table visible, you're going to want to pause this video and go get those things. Definitely want to make sure you have some blank paper or places to work problems with me. We're going to be doing a lot of that today. And then we'll just jump right in. So the way I like to segue into the idea of mole-mass relationships, and you maybe have never even heard of the word mole before, but is with this picture, and you can see a few things pointed out. Recommended daily intakes of iodine, which is a very important element. Iron is a very important one. Vitamin C is another important one. This is not a comprehensive list, but we have recommendations for just about every nutrient our body needs, meaning we need a certain amount every day. If we're talking about iodine, men and women don't need a lot, but we need about 150 micrograms a day. Okay, we know iodine is very important for your thyroid. Whoops. Vitamin C, we need a whole lot more vitamin C. Men need about 90 milligrams. Women need about 75 milligrams a day. So that's on an order of 1,000 times more than the amount of iodine we need. Iron, men need about 17 milligrams. Women, 13 milligrams. And you can see a few different sources pointed out. All of these great foods, great options for getting these important nutrients, minerals, vitamins. But my question is, how do we know, how did we derive this stuff? Obviously, people have sat and studied roughly how much we need of different vitamins and nutrients. Okay, but our body doesn't intuitively know these things. So how do we know how much of each nutrient? Here's a question our body needs each day. Now, before I'm not actually going to directly answer that. Again, just this has come about from people studying the body, how much we need to eat before we're overeating or undereating. We've derived this stuff. But one important and unique thought I want to make is right here, is that our bodies see and process molecules. Okay, it sees vitamin C, it sees iron, it sees iodine. But that's not typically how we communicate, buy, sell, cook. We typically work with units of mass. And indeed, if you scroll back up here and look at these, all of these recommendations, they tell you the mass of vitamin C that we need, or the mass of iodine, not how many molecules of iodine or vitamin C or iron that we need. Here's some further examples. If you go to the store and buy a bag of sugar, you're going to buy, say, for example, a 10-pound bag or a 5-pound bag of sugar. You're not going to buy a bag of sugar that tells you it's got 60 billion molecules in it, right? Here is on the right a picture of I don't know if you can read this, a topical anesthetic spray. So my sports medicine people, my future athletic trainers, PT people, if you have an athlete that gets an injury, you might spray this on that to numb it for a little bit. I don't know if you can, these numbers are very bad. 3.5 fluid ounces in this can of our active ingredient or of our substance. It doesn't say there's 60,000 molecules. So we're used to conveying and communicating in terms of mass, but the body communicates and processes things in terms of molecules. So how do we cross that bridge between mass and then molecules? That's what today's lecture is essentially going to be all about. And my blank down here at the bottom says that the mole was developed to relate number of molecules to mass. So we're going to spend today talking about this idea of a mole. Now, what is a mole? It is a word that stands for a number of items, okay? We're mostly going to use it to talk about a number of molecules or number of atoms. And a mole will relate number of molecules to mass. So guess what? This will be a conversion factor for us, allowing us to convert between molecules and mass. Now, to use the mole, there's a couple of things we need to know. We need to know a molecule's molecular weight, meaning how much one molecule weighs, and secondly, we need to know how many molecules of a given substance are in a certain mass, okay? If we know these two things, then we can do some calculations or converting between molecules and mass. So what is a molecular weight? We said it's about the mass of one molecule, how much one molecule weighs. And to calculate that, you're going to just sum up, get the total of the atomic mass for every atom in a molecule. And this is where we will need, again, a visible periodic table if you want to pull one up on your laptop or your phone to work some of the problems in the coming slides. If we're talking about an ionic compound, we call it a formula weight. If we're talking about a covalently bonded compound, we call it a molecular weight. So going back to our topical anesthetic spray here, here is the reaction that makes ethyl chloride, which is the numbing reagent in our spray. It's kind of the active ingredient. So ethylene, C2H4, and hydrochloride, HCl, can be combined to make ethyl chloride, a topical anesthetic. And we are going to use this as an example. You can do this with any chemical reaction, which is nice. And you can calculate the mass of any molecule as long as you know its formula. Okay, so let's scroll down to the next slide. We are going to calculate the molecular weight of these molecules using their formula. So you need to know how many atoms and what kind of atoms you have in your molecule. So this very first one, for ethylene, we have carbon and we have hydrogen. We've got 2 carbons and we've got 4 hydrogens, and we're simply going to look at the periodic table and multiply the number of carbons and hydrogens by their mass on the periodic table. So for carbon, if you're looking at the periodic table, you should see that its mass is 12.011. 2 or 3 decimals is usually a good rule of thumb. Sometimes there might be certain atoms we round a little bit. We're going to use the unit of AMU, atomic mass units. For hydrogen, we'd say 4 times 1.0, I'm going to say 0.01 AMUs. And then when we multiply this out, for both, we can now get these numbers. Now all we do is add all this together to get the total mass of C2H4, which would be 28.062 AMUs. All right, so 1 molecule of C2H4 weighs 28.062 AMU. Now remember, AMU is a really small unit. So we're going to use a more tangible unit later on because AMUs is just so small it's hard for us to even wrap our brain around. It's a unit made up just to kind of scale down to the size of atoms. Okay, same thing with HCl and C2H5Cl. HCl, you just have 1 each. So I'm just going to write their masses down. For hydrogen, we know it's 1.01. For chlorine, we know it's, if you look at the periodic table, 35.456. You add all this together, and you should get did I do that right? 36.466 AMUs. All right. Then lastly, same idea you probably are catching on here that we would do for carbon, hydrogen, and chlorine. 2 times 12.011. Again, this is right off the periodic table, 12.011. For hydrogen, 5 times 1.01. For chlorine, we just have 1, so it's going to be 35. And when we add all this up, okay, you can throw it in your calculator. I'm going to try to do it the old school way here. Okay. You should get something around this. If I'm off a little bit, I'm not throwing things into my calculator right now. So double check me on that, but that should be about the mass of 1 molecule of C2H5Cl. And as long as you have the formula, you can calculate the molecular weight of any molecule. Okay, so I'm going to scroll down. We have a table summarizing what we just did, which is calculate the molecular weight for these 3 molecules. Kind of the top half of my slide is just a review of what we've already said. But again, I mentioned this idea that AMU is just too small. It's not a tangible unit for us. So if we actually take the unit of AMU and just say grams instead, something really cool happens. Now we have a whole lot more C2H4, like a whole lot more. This is just the mass of 1 molecule of C2H4. Well, if we had 28.062 grams of that, we would have, billions and billions and billions of this molecule, a ton of them. Same idea for HCl and C2H5Cl. When you change the unit to grams, okay, I actually just want to read my statement in red down here. When a substance weighs numerically the same in grams as its molecular weight, the weight of 1 molecule of that substance, then the number of molecules present is called a mole, abbreviated MOL, okay? Now, I know I really haven't still defined what a mole is, and I think that's down on the next slide. But just know, we could say, okay, once I've calculated the molecular weight of C2H4 or HCl or any of these, and I changed it to grams, I could say I have this mass of C2H4 is 1 mole of C2H4. This mass of HCl is 1 mole of HCl, so on and so forth. All right, I think I have another table summarizing this. Yeah, so we're gonna fill all this in. So when the molecular weight is the same in grams, okay, in grams, then we have 1 mole of that substance, MOL. And in just a second, using Avogadro's number, we'll understand that this 1 mole stands for a certain number of molecules, okay? And it actually stands for 6.022 times 10 to the 23 molecules. So if I have a mole of any substance, when I have its molecular weight in grams, I have 6.022 times 10 to the 23 molecules of C2H4. Same idea with HCl. You're just going to copy this number down. And C2H5Cl. If I'm moving too fast, by the way, please pause and rewatch this video. Again, write down questions and notes and things as you go. So let's define exactly what a mole is. There's my fridge. I'm doing this from the comfort of my home today. Sorry, I'm gonna let that shut off. Okay. A mole. Here's the exact verbatim definition. This is going to sound a little redundant to things I've been saying, which is on purpose. But it is the amount or quantity of a substance whose mass in grams is numerically equal to its molecular weight. All right. And then Avogadro's number, which is this giant number right here. This is Avogadro's number, okay? 6.022 times 10 to the 23. This is Avogadro's number. So you need to memorize this for the exam. We abbreviate that N with a subscript capital A. This is the number of molecules or atoms in a mole. Okay, just the same way, my favorite analogy here is just the same way 1 dozen. If I said I went to the store and got a dozen, I think the most popular item is eggs, right? A dozen eggs. If I have 1 dozen of anything, eggs or boxes or cans or bottles of water, whatever, then you automatically know, because this is so common in our culture and our language, that stands for 12 items. So if I told you I had a dozen molecules, you know I have 12 molecules. Well, a mole works the same way. 1 mole equals 6.022 times 10 to the 23 molecules or atoms. Okay. If I said I had a mole of eggs, you would know I had 6.022 times 10 to the 23 eggs, okay? Whatever the item is, we're mostly in this class going to use it to refer to molecules or atoms. But we use this word, mole, the same way we would use the word a dozen, is kind of what I'm trying to say. How big is Avogadro's number? I always throw this slide in just because it does help. You write it in exponent form so often that you can not exactly grasp how large it is. So I like to show this figure, which has all the zeros typed out for you, how large Avogadro's number is. It's 6 with 23 decimal places behind it. It's just an astronomical number. I mean, bigger than any billions and trillions you could imagine. It's an absolutely astronomical, massive number. Okay, so when we say we have a mole of any substance like C2H4, we have a lot of C2H4 molecules, like a ton. So it's a very, very large number. Okay, now how do we apply this word mole and Avogadro's number? How do we use them to do some converting between useful things? Well, last kind of phrase here, new phrase we'll use for the day, introduce for the day, is this idea of molar mass, which is the relationship between mass, grams, right? Or kilograms or milligrams, usually just grams though, and moles. Okay, so a molar mass is the same idea with the way density is a relationship between mass and volume. Remember, density equals mass over volume, all right? And you had units of like grams for mass and milliliters for volume. Molar mass works the same way. Okay, molar mass, which I will abbreviate M, capital M, is equal to the mass or the grams of any substance divided by the number of moles of that substance. It's relating the mass of a substance to the number of moles of that substance. So this would be the molar mass of C2H4. This would be 36.46 grams, would be the molar mass of HCl. We have 1 mole of that substance, HCl, and it weighs 36.46 grams, so that's the molar mass. So if we're writing the molar mass for HCl, we'd say it's 36.46 grams per 1 mole. Does that make sense? And just the way we use density to convert between these different units, we can use molar mass also to convert between grams and moles. All right, which is what it says down here. Conversion factor between mass and number of moles. And then Avogadro's number is a conversion factor between moles and number of molecules. So I'm going to put all this together in a helpful little chart. A lot of students find this very useful for assignments we'll do in the future and for the exam. So if you notice that we have moles in both of these statements, all right? So moles is kind of your middle unit. So I'm going to write it in the middle. So make this chart with me. Put a star by it. You're going to want to memorize this. It'll be very helpful. Now, if we're going to convert between moles and mass, so I'm going to draw an arrow this way. I'm going to make it a two-sided arrow. If we want to convert from grams to moles or moles back to grams, okay, we can do so using the molar mass. I'll write it above and below the arrow because that is the tool, that is the value we will use to convert between moles and grams, right? And then if we want to convert between moles and number of molecules or atoms, we're going to use Avogadro's number. So I'm going to draw another two-headed arrow, and I'll write capital N, subscript capital A, that's Avogadro's number. And that will tell us the number of molecules or atoms. Okay, so the way this looks is 1 mole is equal to 6.022 times 10 to the 23. Remember, start working on memorizing this number. Molecules / atoms or atoms. Okay, so we can use molar mass or Avogadro's number to convert ultimately from grams to moles, moles to number of molecules. So now we're going to do quite a few practice problems. Again, if you don't have your calculator, if you don't have a periodic table, pause this video and go get those things. Do not just watch me do this. Instead, I would read the problem and pause the video and see if you can try it ahead of me. And then, you'll watch me work it out and check your answer that way. That would be the best way to learn this. If you want to watch me do the first 1 or 2, but there's going to be some extra practice, more than we have time to get to on this video, that I would suggest you do on your own for extra. So, first question here. If we have 6.022 times 10 to the 23 carbon atoms, the question here is actually up front. What is the mass of that? So you should recognize this number is Avogadro's number, which means if we have that number of carbon atoms, we have 1 mole of carbon atoms. You could start with 6.022 times 10 to the 23. I'm going to start with 1 mole since I'm trying to get all the way to grams. Okay, I'm trying to get here. If I actually start with moles, I start a step closer than if I start with the number of atoms or molecules. So I'm going to start, since I know how many moles I already have, it's just 1 mole. I'm going to start with the number of moles and go straight to grams using, guess what? The molar mass of carbon. So I'll just write down to start this problem, 1 mole of capital C carbon. Set up a T-chart, or if you hate T-charts, whatever you like to do instead. The molar mass of carbon is this. 1 mole of carbon is equal to how many grams of carbon? This is where you go to the periodic table. You look at the square for carbon. You retrieve that mass, 12.011. We're going to use units of grams. And when you plug it in this way, we see moles of carbon cancel, and we'll be left with grams of carbon. Obviously, 1 times 12.011 divided by 1 is just 12.011 grams. So So if I have 6.022 times 10 to the 23 carbon atoms, the mass of that number of carbon atoms is 12.011 grams. And you could do that for any element on the entire periodic table. All right, this next problem is going to be a little bit more involved. And we're going to use our whole chart. And when I say whole chart, I mean this whole thing we wrote up here. We use this whole thing, okay? All right, it says the chemical formula for aspirin is C9H8O4. How many molecules are in 25 grams of aspirin? So this is what we're going to start with, 25 milligrams. And we're asked to convert that to molecules. So you want to go to your chart and say, where am I starting on this thing? I'm starting on the side with mass, and I'm actually not even starting with grams. I'm given milligrams. So the first thing we have to do is convert to grams, and then we're right here on our chart. We're on the left side. So now we can just follow our chart along and convert until we get to number of molecules or atoms. This is kind of how the chart works. So I'm going to write a little concept map to tell us our steps. The first step is we'll convert milligrams to grams. That'll be step 1. Step 2, we're going to convert grams into moles using the molar mass of aspirin. So we're going to have to calculate the molar mass for this. Just like earlier, we calculated the molar mass or the molecular weight of, C2H4 and HCl. We'll do the same thing here for C9H8O4. And then step 3 is we are going to convert moles to molecules. How will we do that? Well, we'll go back up to our chart. It says NA, which does not mean not applicable. It means Avogadro's number. Okay, so we know how to convert milligrams to grams, right? That's easy. Unless you forgot, and then it's not easy. So you're going to want to remind yourself of different prefix relationships. How many milligrams are in 1 gram? Hopefully you remember it's 10 to the power of 3. Secondly, we're going to say, okay, how many grams of C9H8O4 is in 1 mole of C9H8O4 of aspirin? And to plug this in, this is where we plug in the molar mass. So we're going to calculate the mass of this in grams, and we know that will be equal to 1 mole. So let's do that over here on the side. I'm going to zoom in so that you keep the formula visible. We have carbon, hydrogen, and oxygen. Carbon, we have 9 of them. Again, I'm just looking at these subscript numbers. Hydrogen, we have 8 of them. Oxygen, 4. And we're going to say times their mass on the periodic table. For carbon, we know by now, 12.011. Now we're just using straight units of grams. For hydrogen, 1.01 grams. And for oxygen, if you look at the periodic table, it says like 15.999, but I just use a flat 16. And then we can add all this up. So grab your calculator and double check me. 9 times 12.011 plus 8 times 1.01 plus 4 times 16. And I got 180.179 grams. This is how many grams is in 1 mole. This is how many grams per mole. In other words, how we say it. So we're actually going to take this value and plug it in where my molar mass goes. This is the molar mass we just calculated. Boom. So I'll plug in 180.179, and that's for every 1 mole. So we just did steps 1 and step 2. So now we got to go moles to molecules. So step 3, I want to cancel moles and convert to molecules. So remember this statement that I wrote right up here? Let me erase some of this. This statement right here in this black box. 1 mole is 6.022 times 10 to the 23 molecules. So we're going to use that relationship now to convert from moles to molecules. And aspirin is a molecule. So for every 1 mole of aspirin, we will have 6.022 times 10 to the 23 molecules of aspirin. All right, so this was step 1, converting milligrams to grams. Again, go through and cancel out every unit that cancels. Milligrams cancel. Grams cancel. Moles cancel. And we're just left, the only one that doesn't cancel is molecules, which is what our question's asking for. This was step 2. This was step 3. Okay. All right. We calculate this. 25 divided by 1,000 divided by 180.179 times Avogadro's number. You should get 8.356 times 10 to the 19th. Okay. And that's typical. When you're asked how many atoms or molecules, probably be a pretty large number if you're dealing with a tangible mass, like 25 milligrams. So that answer and how big it is should not surprise you. Usually you're dealing with pretty big numbers when we're calculating numbers of molecules. Okay, here's another problem. Again, I encourage you to pause the video, read this, try to work it out, at least pieces of it on your own, and then see how you do watching me do it. So this problem says the average daily recommended intake of carbs, meaning glucose molecules, for a healthy adult is 6.67 times 10 to the 23 molecules per day. This does not include intake of added sugars. Okay, just how many base level molecules of glucose our body needs a day. So the question is, how many grams of glucose does this equate to? All right, so we're given molecules. This information right here is units of molecules. And we want to know grams. So think about the chart, which is this right here, grams to moles to molecules. Okay, this time we're starting over here. We're starting on the right side. And we're asked to go all the way to grams. So we're just going to work this problem with the same types of values, like molar mass and Avogadro's number. We're just going to work it in reverse to the one we did with aspirin above. So I'm going to start with 6.67 times 10 to the 23 molecules. Set up your T-chart. First, to go from molecules to moles, this will be step 1. We need Avogadro's number, which says there is, this time I'm trying to cancel molecules, so I'm going to put it on the bottom, 6.022 times 10 to the 23 molecules. And put this in parentheses because I want you to know when you divide by Avogadro's number, you have to, in your calculator, put it in parentheses. So if you write it in parentheses, that will help you remember, oh, when I divide by this, I've got to put it in parentheses. This is 1 mole of glucose, okay? 6.022 times 10 to the 23 molecules of glucose is 1 mole. And so that's step 1. Now we need to go from moles to grams. Well, to do that, we need the molar mass of glucose. And to do that, we need the molecular formula, which I did not even give you guys. Glucose is C6H12O6. All right, on the exam, I would have totally given you the formula. All right, so we know 1 mole of C6H12O6 is going to be equal to X amount of grams of C6. This is glucose. So again, we need to calculate the molar mass. So I'm going to come down here, carbons, hydrogens, oxygens, 6. For carbon, 6 carbons times the mass on the periodic table, units of grams. 12 hydrogens times its mass on the periodic table, units of grams. 6 oxygens times 16 its mass on the periodic table. Add all this up. And I got 180.186. This is how many grams of glucose per 1 mole. So I'm going to plug this right in here, 180.186. All right, now let's double check. Do our units cancel the right way? Molecules cancel, moles cancel, and all we'll be left with is grams. So now we need to do the math. So I'm going to start with 6.67 times 10 to the 23. Now, I don't have to put this first number in parentheses because it's on top. But because this number has a multiplication sign within the value, within the number, I'm going to hit divide in my calculator, and then I'm going to put it in parentheses and say divide by 6, in parentheses, 6.022 times 10 to the 23rd. And then I'll say times 180.186. And I got, for my answer, 199.57. This will be grams of glucose. So our body needs 199.57 grams of glucose a day. Now go back and think about how much iodine and vitamin C we need. We only need like micrograms and milligrams. We need a whole lot more glucose, all right? It's just that with all the added sugar in our food, oftentimes when you're eating a lot of, the farther you get away from like fresh produce and meats, the more often you are to go over this value in our diet. So pretty cool problem. This is using all the steps. There's a lot involved here. I told you it's a lot of math today, so pause this and rewatch it if you need to. I've got more problems. I'm going to let you work these on your own. Take note of what you're given and then what it's asking for. Use the chart. Use molar mass. Use Avogadro's number. You don't necessarily always need Avogadro's number. For example, if both of these problems, you're given either grams or moles, so you're not ever asked for molecules. You're not ever given molecules. So you actually won't even use Avogadro's number in either of these problems. Up here, we did use Avogadro's number because we were either asked to, calculate a number of molecules or we were given a number of molecules. But if the problem is just between grams and moles, then you'll just need molar mass for these, not Avogadro's number. So try to do those, and please come to me with any questions you have. Okay, that gets us to our next topic in Chapter 6, which is this idea of mole ratios. Okay, so I'm going to read this statement at the top here, which outlines our chemical reaction. Hydrogen reacts with nitrogen to make nitrogen trihydride, okay, also known as ammonia, which is used and made industrially. It's used as a fertilizer. It's used all kinds of ways. And we are told here in our equation that we need to balance it. So let's look. I've got 2 nitrogens on this side, and I only have 1 here, so I'm going to put a 2 in front of NH3. This 2 would be multiplied by that 3. That would give me a total of 6 hydrogens on the product side. So if I come back and put a 3 here, now I have 6 hydrogens on both sides, and I should be balanced. And that's what you see below, okay? Coefficients of 3, 1, and 2, which means I'm going to read these statements. This number of moles of hydrogen, 3 moles of hydrogen, reacts with 1 mole of nitrogen to yield 2 moles of ammonia. Okay, that's how we can read that now. And we think of these values as a proportion or relationship between reactants and products. And we can write out mole ratios between any reactant and any other reactant, or any reactant and any product. So if I wanted you to write a mole ratio, a ratio just between hydrogen and ammonia, NH3, it would look like this. For every 3 moles of hydrogen that I put into the reaction, I would get out 2 moles of NH3. That is a mole, that's your mole ratio between hydrogen and ammonia. We could also write one between nitrogen and ammonia. For every 1 mole of nitrogen, N2, we write it N2 because these are diatomics, right? Hydrogen and nitrogen are diatomics. So you can't just write H and N. But for every 1 mole of nitrogen I put in, I will get out 2 moles of NH3. Okay? And then lastly, for every 3, we could write one between our 2 reactants. For every 3 moles of H2, I will get out 1 mole of N2. Or I will need 1 mole of N2 to react with every 3 moles of H2. All right. I'm going to pause this video and pick up with a second video starting here on mole ratios as well in just a minute.